so page 6, I've been waiting to do since we talked about energy, because this is a really unique and creative on College Boards. It's not maybe a typical type of situation, but in 2018, this was number 5. That year, it was the paragraph response. So part B is going to say, write a paragraph. So not only are we getting that practice, but there's a collision, there's a spring, there's changes in position, changes in speed. We've got energy here. This is like a triple topic kind of question. And so by May 12th, make sure you're ready for those. Practice enough of them. Are they going to give you a free response that's only momentum, only kinematics? No. Kinematics may be one piece of the 4-part question, okay? They love doing it, blended topics. And so here they give us a picture. They tell us it's 7 points. Again, just to prepare you for the AP exam on May 12th of the 5 free response, note to self, you'll have 3 short. They're each 7 points. And then you'll have 2 long. And those are each worth 12 points. Okay. You want as many points as you can. Please, please try and pace yourself so that you try something on every problem, okay? This year in particular, 2018, I believe out of the 7, I have it printed, hold on. This question, the average in the nation was 1 out of 7. Now, they didn't go into detail, okay? That's just from College Board, their stats. And so it's everybody who maybe ran out of time and had nothing written down to somebody who wrote a whole paragraph that was totally wrong. So 1 out of 7, don't forget about number 5, okay? If you look at number 5 stats, it's not always the paragraph, but I think some people just don't get to it. 1.6 out of 7, 2.2 out of 7. 1 out of 7. So try to pace yourself. This AP exam is not going to be like, I think, history and or English, where so much time has passed. You should move on to the next passage. That's in some AP exam. You just say 90 minutes, go. You have 30 minutes remaining. You have 10 minutes remaining. When you hear that 10 minutes remaining, you know, if you haven't touched number 5, you may want to go to it. Good deal? Okay. And so we've got block P of mass M, rats, no numbers. It's on a horizontal frictionless surface, yay, and it's attached to a spring with a spring constant, lowercase k. The block is oscillating with a period TP and an amplitude AP about the spring's equilibrium position, XO. And notice they label that in the picture. And so this is the equilibrium position. Now, I kind of wish AP gave us a picture without block Q. I know you see 2 pictures there and you're like, oh, they look the same. On the real exam, this is all spaced out. The second picture was actually on the second page. So if you ever work these and you're like, oh, I need more room, you're given more room on the real exam. But I wish they gave us kind of a before we have Q. And then, so here's part 2. A second block, Q, which has twice the mass, is then dropped from rest, and it lands on block P at the immediate instant that block P passes through the equilibrium position as shown above. Now I think, oh, this is a perfect scenario, physics land. What are the chances, right? But as block P goes through equilibrium, boom, Q falls on P, and it says it immediately sticks to the top of block P, and the 2-block system oscillates with a period PQ and an amplitude of AQ. And basically the 2 questions you're going to answer, compare their periods, compare their amplitudes. Compare the 1-block period to the 2-block period. Compare the 1-block amplitude to the 2-block amplitude, okay? A, determine the numerical value. How are we supposed to get numbers if they didn't give us numbers to start? Well, don't stress about that. Let's just focus on what we're solving for. It's not what is the period, it's compare the ratio. And so PQ is our second scenario. That's kind of the new one, right? And so let's set it up. PQ over the period of P alone. Well, this is a mass on a spring, horizontal frictionless surface, thank you. So what equation am I going to plug in for both of them? What's the period of a mass on a spring? 2 pi times the square root of m over k. And so it's the mass of PQ over the spring constant PQ, all over same thing, just with p's. What do we notice? Just pi? 2 over 2 cancels as well, right? That's what you meant. Good. What about the spring constant? Is the spring any different after the collision? No. So it's the same. If KPQ equals KP, then what can happen? Then it can cancel. And so what we're left with, it's a ratio of the square root of their masses. Now, this isn't the final answer. They said a numerical value. And actually, they did give us some numbers for the masses. And so what's the mass of the system P and Q? 3m divided by the square root. What's the mass of P alone? Just m. I'm going to go in and show my coefficient there, the 1m. M over m, what happens? Cancels. So final answer, the ratio of the new to old period is just square root 3. Square root of 3 to 1, if you want to say, but square root of 3 is all they want. They gave 1 point for all that. Okay. Now, I could very well see College Board saying, you know, if this was similar, you know, in a new question, maybe it could be worth 2 points. 1, does the student use the correct equation, right? Do you implore, you don't want just to put an answer. They usually don't give points for answers alone. It's the work leading up to it. But on this one, in 2018, it was 1 point for the final answer. Good deal? No, this was actually on the key. Yeah, I usually take it and I would go, oh, 1.7 to 1. They would accept either one. I'm just used to most physics problems, taking it to the decimal. I think AP1, since they do less numerical solve, if you didn't have a calculator, you may not know what that is, right? Okay. Okay, you okay? If you need to step out, you can. All right, so then on the next page, they duplicate the exact same picture. Now, I just want to give you a warning. Sometimes they'll make a change to the picture. So don't assume, oh, it's exactly the same. But here it is. They literally say it's reproduced above. How does the amplitude of both blocks compare with the original amplitude when it was just object P? Is it less than, equal, or greater than? By the way, do you think you're going to get points for checking the box? Most of the time, no. 99% of the time, no. I think I've seen one question during 1 year, they actually gave a point for checking the box, but one. So it's very rare. Now, better safe than sorry, right? I don't start out by checking the box. The box should be your conclusion, right? And so I'm going to save that checkbox, and you're not automatically supposed to know the answer. You got to go through the steps. So again, this is a 7-pointer. I told you A was worth 1 point. How much is B? 6. I got to write a paragraph about this. Now they do tell you it can contain diagrams and equations. By the way, you can get points for some physics that you have in equation form. It's not like you have to have a full-blown paragraph and you can't show equations. In fact, most physics people start with equations because it's founded on physics principles. Now, the last year grading, I actually graded the paragraph and they said a minimum, if you had supportive work, a minimum of 3 sentences, okay? And so kind of in that spirit, in a clear, coherent, paragraph length response that can contain diagrams and or equations, explain your reasoning. So support, CER, make a claim, have your evidence and connect it. Make sure it reasons that answer. Clear, coherent, whoever's reading your paragraph shouldn't be confused when reading the paragraph, right? You got to be able to speak physics, communicate physics, make it flow well, okay? Okay, so what's going on here? We did the period business, check. The B is actually the old stuff, okay? There's a collision. What should be going through your head? What big idea do we use for collisions? And so here we go, y'all. I'm not going to start with my paragraph. I'm brainstorming right now, okay? Maybe I'm going to do it right here. If there's a collision, what should be going through your head? Conservation of momentum. Okay. And then we have a spring. Now springs, we have forces, we have energy, we have simple harmonic motion, right? And it's all kind of blended here. So because of the spring, and I'll simplify it for us today, we're going to be using conservation of energy and that SHM with our amplitude business, okay? We've already done the period piece, but to bring in the idea of amplitude there. And so before they oscillate together, they have to collide. But let's look at P alone. So let's do conservation of block P alone. So this is before. And so we don't have a collision, no momentum to consider, but what energy is conserved if it's just P going back and forth, back and forth, back and forth, back and forth? Yes, mechanical energy. What varieties of our mechanical energy would we say is equal? Think of your extremes. They talked about equilibrium. What kind of energy do we have at equilibrium? Kinetic. And so KE max at equilibrium, just so we know, is going to equal, well, what about when I come to a split second stop? What did all that energy go into? What kind of potential? Elastic or spring. There's no height change of P alone, right? Oopsies. And so it goes to elastic maximum. And this is at one of the peaks, left or right here. And so we get 1/2 mv squared equals 1/2 kx squared. Okay. Couple things. What do you notice? 1/2, 1/2. You can cancel, right? We're not really solving numerically. We're coming up with comparisons, so it's fine to do this. And then I'm going to substitute the mass of P, okay, which is going to be just M, right? They said it's just M. That V I'm going to keep. And then K is okay. What can I plug in for X? Max. Say again. A for amplitude, okay? And that's what we're trying to find. And so amplitude, I'm gonna leave it in the square because to do the comparison, you don't need to take the square root, but it would be that mass times velocity squared divided by spring constant. So what's gonna change when block Q falls on block P? Mass is gonna change. Do the others stay the same? Right, so the velocity is going to be different. This is now a collision. We're going to have to go do conservation of momentum. Tell me about the K. That's the only thing that's going to stay the same, okay? And so we know mass is going to increase when block Q falls on, but we need to pause and go do conservation of momentum So now we have the collision of P and Q. Let's go find that new velocity after the collision for P and Q. And so conservation of momentum in the beginning, and remember, momentum is a vector, right? So the oscillation, we really want a horizontal velocity. Do we care how fast it's moving vertically? No, it's going to be stopped by the surface, right? And so some of that energy is going to be lost, we know, due to the collision. Y'all remember heat loss, right? Collisions, you also have to remember, they have heat loss. Ooh. What kind of collision? If they stick together. Completely inelastic, right? So this is a completely or perfectly inelastic collision. And that means you have the most heat loss. So that's why the vertical momentum is going to kind of disappear. We don't have it after the collision. Most of that vertical momentum is going to go into the heat loss, okay? Okay. And so vector quantity, focus on the horizontal. So the net momentum before the collision in the horizontal direction is equal to the net momentum after the collision in the horizontal. So just a reminder, technically momentum's conserved in 2D. I didn't do that with energy. Does energy care about direction? No, it's scalar. So just a reminder, energy is scalar. It didn't matter what direction any of that was. So before the collision, it's just block P going. And so the mass of P, its initial velocity, plus 0 if you want. Block Q is moving vertically, but this is a conservation of horizontal momentum. After the collision, they stick together. There's a combined mass. And then this final velocity after the collision, isn't that what we need for the energy statement for the system? That's the velocity it'll oscillate through equilibrium with. And so we don't have numbers, but we have something. Mass of P is M, right? And before the collision, do they tell us V? Oh, it's a ratio. So I'm just going to say VI is going to be V. We'll get it in ratio form. How about that? And then equals, what's the total mass of our system after the collision? 3M. And here's this VF after the collision that we're trying to solve for. And so mass cancels mass. The final velocity for PQ after the collision is going to be 1/3 of the velocity of P alone. Okay. And so what about the energy statement for blocks PQ? And so block PQ will still have that mv squared, but it's PQ's mass equals PQ's velocity. Spring constant's the same, and we're looking for that new amplitude PQ. Plug in some numbers. Mass of the system, 3M, we already said. The velocity is going to be 1/3 that of P alone. And so 1/3 V, careful, what's 1/3 squared? 1/9. So I end up with 3mv over 9 equals K A squared. Again, K is going to be the same. So pretend it's, factor of 1 in each case. And so 3 over 9 is going to reduce to 1/3. Okay, and divide by K if you want, but APQ compared to AP alone is going to be what? More or less? You're comparing these two numbers. Less. So PQ amplitude is going to be a third less the amplitude of P alone. Have I written a sentence?
No.
I have an answer. So could I just leave it and walk away? I mean, you'd still get some points, okay? You could actually, I'll show you the root. Well, for time purposes, I'm not gonna go through the rubric, but true story, you could get some points for just showing the work. You just won't get full points, okay? And so to get full points, we don't even have to check the box. Let's write our sentences. I told you at least 3.
Should that be something you come back to because you have time?
Yeah, that's a good test taking strategy. Okay, so something to come back to if you have time. I think if I remember the rubric correctly, I think you can get 5 or 4 points out of the 6 available. But let's go on and try just the spirit of what we did, right? You don't have to write out the math with sentence form, but I would say your 3-sentence minimum, 3-sentence minimum. And by the way, I do abbreviate a lot. On May 12th, my abbreviation may not be the same as the graders, right? So do your best. When you're writing sentences, try to write it out, okay? And please write neatly. Sloppy, small, all over the place work, you jeopardize losing points. So write neatly for anybody, young or old, experienced or not so experienced to read, okay? And so one of the first big ideas, y'all, they're looking for big ideas in physics, right? We had conservation of momentum, conservation of energy. There's 2 sentences to talk about, right? And so using conservation of momentum, we can go with the final velocity of the PQ blocks, and they've already abbreviated P and Q, so that's kind of defined in the problem. The final velocity of the PQ blocks is less than the velocity of P alone. Right? That's what we've discovered using conservation of momentum. And then using, and notice I'm doing some bullets. That's totally fine too. It doesn't have to be your English traditional paragraph. You can put your sentences in bullet form, okay? Using the conservation of mechanical energy, the kinetic energy of the system, PQ. Did we? I don't know if we made that comparison. Hold on. The kinetic energy of the system, PQ, is more or less. Well, we did. If you just look at the mv squared compared to the mv squared divided by 3, look at everything on the left-hand side of those equations. Ignore the K, that's not part of kinetic energy. Who has less, or PQ has less kinetic energy than that of P alone? Is less than P alone. And just because I didn't write it out fully, I'm going to do that now. KE of PQ is 1/2 that 3m and then v squared over 9. If you want to simplify that, 1/2 part of the equation, where P alone is just that. So I did that for your sake. I didn't spell it out exactly that way prior, but we do have the work to support it. And then kind of a subset or continuing with conservation of energy, if PQ has less kinetic energy, tell me about the elastic energy. Kinetic energy converts to elastic or spring potential energy, tomato, tomato. Therefore, the elastic potential energy of PQ is less than the elastic potential energy of P alone. And maybe one more step, either another therefore, or I'm going to do another bullet. US is equal to 1/2 KA squared. So with a constant K value, the amplitude of PQ is going to be less than the amplitude of P. And if you're confident, then you go back and check the box, right? Now, note to self, on paragraph responses, it doesn't matter what you check, they will read your paragraph. It's worth so many points, they're going to read it. If you write it, they'll read it, okay? On the short answer type questions that we've seen in the past, if it's a checkbox and then just says explain or justify, they're just looking for one or two sentences. You really need to make sure you're confident before checking that box. Because in some of the problems in the past, if you check the wrong thing, they don't read what you write. It's just one or two sentences, right? And so if test taking strategy, if you're not sure what to check, don't check. But always focus on trying to explain. Even if you can only get to, y'all, you would still get some points if you talked about conservation of momentum and that it's going to slow it down, okay? That the system PQ would be traveling less. Right there, that little recognition, 2 points, okay? So don't think, oh, I don't know how to do 5 or 6 things. I shouldn't even try. No, try, you might get something, okay? Okay, we got just enough time to get one more question started. Okay, again, if you want to see the rubric, it's in the Canvas key, or you can go to the College Board website, 2018 scoring guidelines. And so I'm going to skip over a lot of pages just to show you kind of what's in here. You'll know they're always full of practice, right? That's for your benefit, not ours. Here's some multiple choice practice. If you're like, I'm not going to go to AP Classroom, here's some, right? 9, 10, some more. These are older. And so this is technically from B, but physics is physics. Okay, here's a variable response. That's a lab-based response. You're still going to have those. And then kind of just the big ideas that we've discovered or looked at. And then NIMSIs. So NIMSIs are made with the AP exam in mind. And so they always do kind of pre-assessment, some cliff notes. So those of you who don't like reading 30-page chapters, maybe you can read 2 pages. Some more multiple choice. Page 17 is the one I want to get started because 2 reasons. Is this a spring? Is this a pendulum? No. So I told you 95% or whatever, most of your simple harmonic motions in textbooks on the AP exam are going to be springs and pendulums. But there's a small chance they'll throw something at you. When I saw this one, I was like, ooh, it's a diving board. I mean, it's not really, but you could look at a diving board as an object in oscillation, right? And so marble in the bowl, all these different back and forth, back and forth, back and forth. As long as it has an equilibrium position, then you have oscillatory motion, right? Okay. And so this one, another reason it's good to practice, F2 is technically going to be your lab-based question. It's another long question. So in the AP exam, this one's a 12-pointer. You'll get 25 minutes to try this. Now we don't have 25 minutes, so we're going to try and quickly do 1 of 2 pages. A student is given an aluminum ruler along with other commonly available lab equipment. So notice they don't really spell it out. And I know you haven't opened my cabinet to see what's available. Is Allen equipment common? No, we're actually fortunate. We have a lot of technology here. Okay, you don't have to answer this with technology. You can old school it, okay, with non-technology. The student fixes one end of the ruler or the board to the edge of the table as shown in the above left. Notice that some of the ruler is hanging off the table, right? Some is attached. So they glue it, they tape it, they bolt it. Somehow it's fixed. When the student fixes a small mass to the free end of the ruler, oh, I didn't finish the other sentence. L. Do they define L as the length of the ruler? No, L is how much goes over the edge of the table, okay? So careful. I wish whoever made this question had not made it a ruler. I wish they just said a thin board, right? This ruler is not going to be used for measurement. This ruler is just the platform. It's the diving board, okay? Then we're going to put a small mass on the free end of the ruler, like shown in the right, so that the ruler sinks down a small distance, y as shown above or to the right. Now, have they moved it yet? Have they mentioned moving? No, so I don't have an additional mass right here, but I do have a ruler. If you put a mass on the end, it's going to depress, right? It's going to sink down. Y'all, that's your new equilibrium. Anytime you make changes, but it's still just resting there, that's your equilibrium. And so this, what they label as y, is going to be your distance of stretch or compression type to equilibrium. The student notices that if the mass is disturbed, in other words, if I hold this ruler one end, I don't have a mass, but it's the same as like flicking. And no, I'm not going to pass rulers around because when students flick a ruler, they break, right? And so this is all we're looking at. If you can see the end of the ruler, it oscillates further down and it goes above the horizontal position, right? Oscillatory motion. It doesn't keep going forever, but it has that back and forth about an equilibrium position. All right. The student asks themselves the question, is the periodic motion that they see of the mass considered simple harmonic motion? The student then determines for themselves or decides to perform an experiment to answer this question. And so they this page breaks it up into steps 1, 2, 3, 4, but collectively, what equipment are they going to need to use to perform an experiment? 2, outline the procedure to talk about the measurements needed to answer the question. So we've got equipment. What are we going to measure with that equipment? Part 3, how are we going to analyze the data once I've collected it? By the way, how do physics people, experimenters, analyze data? Okay, maybe linearization, but we graph, right? So have graphs in your mind. And then part 4, just because it's the first part, it says create that example graph. So if you didn't think graphs in part 3, maybe now you are, okay? Create an example graph that the student could obtain to indicate if it's simple harmonic motion. Now, by the way, with lab-based questions, there's typically, they do this on purpose. It's not one procedure for all thousands of students. Usually they have it open-ended a little bit so you can do one of maybe 3 ways. This one, the key for NIMSY, gives 3 different approaches. So I'm gonna go back to part 1. You tell me what's running through your mind. What data would we need to collect in order to figure out, is this simple harmonic motion? Is the periodic motion of the mass, so focus on mass, also simple harmonic motion? How do we figure it out? It's not a mass on a spring, but it's the mass on a springy platform, yes? Is a certain equation running through your head? Seems like there should be. With the exam next class, there should be. We've used it for 3 classes now. It's on the formula chart, spring, mass. TS equals 2 pi times the square root of m over k. And now you're like, oh yeah, right? Now k is a spring constant, so we kind of got to loosely use this equation. Really what we're trying to figure out is t, the period, proportional to the mass. Now we know the equation has a square root, but maybe you don't know that, right? And so this is really what we're trying to question. So let's see, how would I make measurements for this? Well, mass, what equipment would we need to use? A scale to measure the mass. What other equipment? We see time's important. Uh-oh, how do we measure time? Stopwatch. And so a stopwatch to measure time. Now, let me be honest. What have I told y'all about stopwatches in real life? A lot of user error, right? Reaction time. So you probably don't want to time one oscillation, but if you were watching me flick the end of that ruler, 3 oscillations still happens real quick. And so an option, and some of you did this in the pig lab, some of you in the ball drop lab. What if we take video and do like a slow motion analysis, right? That is a viable option, okay? For things that happen real quick, you can do time-lapse video and do measurements of time. Good deal? Now, there's one more thing I would add, and it's not in the equation, but later we're going to produce a graph. We're not changing the mass, but we're going to have all these periods. What else might we want to plot with timing of oscillation to see if it's simple harmonic motion? Do you remember what the graphs of simple harmonic motion look like? It looks like a wavy, right? And so what other piece of information might we want to collect and future plot so that we see if it's simple harmonic? Say again. Go basic. Doesn't just seeing the position of the object, okay, getting the position. So I would add in here, so I'm going to keep going, blend over. Use another ruler to measure the amplitude, right, of the oscillation. Good deal? So we've mentioned the equipment. I've actually kind of already started answering part 2, outline a procedure. We know what to measure and what equipment to use. The other good thing to point out, guys, when you're a real life person, one measurement's not going to do it. What's a good scientist do? Multiple trials. Always include that in your procedure. Uh-oh. There's a timer going off. But try to finish this one. Check the key on Canvas. And then we got our exam next class. So I'll see you Tuesday for our simple harmonic motion exam. Right?
What happened? I said, come on, not during